linear least squares, and some applications. So we'll talk about Gauss system for linear equations, talk a little bit about how to do Gauss elimination, homogeneous systems, very briefly look at the relation of LU decomposition, determinants, and then talk about least squares, and then we'll look at applications of first fetting to a femoral head for an implant, and then talk about triangulation. So it's a motivating problem. Linear systems arise in virtually every area of science and engineering. Things as millions of equations can be done. We've already seen the Google billion-dollar eigenvector, for example. So when we go to work on these, we have a bunch of, in this example here, we might have a bunch of triangles. And these triangles describe the object, but you can sort of see there's a lot of parts of these triangles where they're very small and thin. This makes them very inefficient to render and difficult to work with. So we might want to have a smoother triangulation. This is not the same as playing with a shading. This is actually changing where the triangles are in 3 space to make them a better match for what we want to do with our rendering. And we'll come back to this at the very end of the chapter. This leads to lots of equations. So in general, our n by n linear set of equations, right? We have n by n matrix of unknowns, n unknowns on our right-hand side. In fact, this could be n by m. It doesn't have to be square. A is called the coefficient matrix for our linear solution. In general, as we go to higher dimensions, we've already briefly talked about this idea, but let's talk about the geometric principles. If we think about in 3D, a bunch of column vectors, so if we think of each of the A in this matrix as being column vectors, A1, A2, dot, 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 up to AN, we can write, the question is, can we write B as a linear combination of the AI? So U tells us the linear combination of how much of the first vector, how much of the second vector, how much of the third vector gives us B. And it can be in 3D, it can be in 50D, it doesn't matter. Think of each of the AIs as defining a column vector, which is a vector in that dimensional space, and then we're asking the question, what linear combination of those vectors gives us B? If AI is truly, in this case, a 3D unique thing, form a tetrahedron. So if these 3 are linearly independent, they'll form a tetrahedron, we get a unique solution. In general, in higher dimensions, we have to make sure they solve, they're all linearly independent. If they all lie in a plane, then there is no solution, and B is not. Sorry, if they're all in a plane and B is sticking up, then there's no solution because these guys can't get out of the plane. If they all lie in a plane and B lives in the plane, then there's not a unique solution. So we have a bunch of different ways we can look at this. So in general, we have that if the AIs form a non-zero n-dimensional volume, then the linear system in n dimensions is uniquely solvable. If the AIs span a k-dimensional subspace, where k is less than n, then the non-unique solution exists if and only if B is in that subspace itself. A linear system is called consistent if at least one solution exists. So one or infinitely many is called a consistent solution. And those are the things we want to be able to look at. So in sort of another motivational problem, let's look at a classic example of trying to fit a polynomial to some data. So if we're given some observations at different times, and at those times we're told the value of our function, and we're going to say for some reason we believe our polynomial is a fourth degree polynomial, and then we want to interpolate the data, and that'll give us the ability to estimate the value in between these observations. So we do that by, in this case, taking our time variable, t, and we're going to build a matrix of t, t0, t squared, t cubed, t to the fourth, at each time interval, t0, t1, t3, up to t4. That's our coefficient matrix. Why? Because I've just evaluated this polynomial at a bunch of locations. So at every point, it's c0 times 1 plus c1 times t1, or c1 times ti, c2 times ti squared, and so on. Right? This gives us our coefficient matrix equals the values. Now we have this matrix. We simply solve for this, and we'll get our values of ci that fit that polynomial. We'll come back to this problem again later. So in general, in higher dimensions, we can think about how to solve it. So we have this term of Gauss elimination we sort of already talked about. Remember, for our 2D by 2D example, we have some general, we have our matrix, and the forward elimination state is to transform this to an upper triangular matrix with a shear. And by a shear, what we really mean is we're going to take a linear combination of these two, the 2 rows, and update the system. So if we shear it by minus a half and 1, 1, 0, that matrix there, we can shear this 2, 4, 1, 6 into 0, 4 on the bottom row, right? Which is really just 1/2 times the first row plus 1 times the second row, and it disappears. And so in general, we're going to have row 1 goes to row 1, or sorry, for this example, we're going to have row 1 goes to row 1, and row 2 goes to row 2 minus 1/2 times row 1. In general, our Gaussian elimination, forward elimination step is to find a shear matrix, which is going to take a linear combination of rows and replace the leading elements with zeros. Once we have it in upper triangular form, we just apply back substitution, we read off the values, stick them back in, and gives us the right. Now we can interpret all of this as a mixed set of steps. So the last step involves a scaling, so that we get the diagonals to be 1, then we can just read off the values. So in the end, we have two matrices. We're going to take the left-hand side and the right-hand side of our equation, A equals B, pre-multiply by S1, our shear matrix, and then pre-multiply by S2, which allows us to then get what we need for our answers. Now, that's great if everything works out, but every now and then we have to do this thing we call pivoting. So if you remember, pivoting was to reorder things so that the largest element is in the first column, right? And in the element we're going to try and eliminate. So here we have 1, 6, 2, 4. We swap the rows, we get 2, 4, 1, 6. And if I just swap the rows, I don't have to do anything. A row exchange can actually be represented as a permutation matrix we multiply in front. So this will swap the rows. So we just take P1 times U plus P1 times that times B. So here, because our right-hand side was 4, 4, you didn't see it, but if it had been 2, 4, it would be 4, 2. And then we do Gaussian elimination as before. So now we've done our pivoting, and we can combine them. And in higher dimensions, we might have to pivot multiple times. It also, so here's a 3D example. We first define a pivot because our first row is a 2. We want to have one of our 4s in the first row, so we swap the first 2 rows. Then we zero out things by making row 2 go to row 2 minus 1/2 times row 2, and row 3 go to row 3 minus row 1. Right, so that gives us the following Gaussian elimination matrix, which you could actually view as 2 shears, but here we've just sort of combined the 2 shears into one matrix that gets our first column to have 4, 0, 0. This G1 is called the Gauss matrix. It's a set of shears to reduce the entire column to 0. Continue that example. We don't have to do any pivoting. So for the second row, because they're both second column, they're both zeros. So now we just do the shear. We get rid of this last element. We get row 3 as row 3 plus row 2. Combine those 2 rows, and we get our final upper triangular matrix, which it's upper triangular matrix. Things are 1 down the diagonal, so it's ready for back substitution. We just fill them in. Because all of the diagonal is 1, we don't have to do a separate scaling. So that gives us our solution. We can go back to this. And again, you can verify that this matrix times these values equals our original right-hand side. So in summary, in higher dimensions, Gaussian elimination is forward elimination, combinations of pivoting and shears, which again, we sort of collapse into a Gauss matrix if we want to, plus back substitution. These element row operations of Gaussian elimination, pivoting is an exchange, shearing is adding a multiple of one row to another, and scaling is scaling multiple rows. These, if done to both sides, don't change our solution space. So again, think of it as we're just going to have all those matrices out in front multiplied. So overall, to summarize our Gaussian elimination with pivoting, we're going to be given an a matrix n by n matrix A. On the right-hand side, we want to find the vector u that solves this. So we initialize our n by n matrix G for I equals 1 to n minus 1. It's counting what column we're going to work on. First, we're going to find the largest absolute value in this column. And if AJ, and if it's not, we're then going to exchange the rows. So if it's not in the right place, we run through and exchange the row elements. And if AJJ is equal to 0, the system's not solvable. So if the highest element we get out after this is all 0, then we've reached a place we can't move forward on. Our forward elimination step, we go for j plus 1 to n. So we're going to work below the diagonal. We're going to construct the multiplier for this row, which is always just the ratio of aij and ajj, divide by what's on the diagonal we're trying to solve, set aij equal to 0, and then subtract gi times our jk row after this from our row. We're just figuring out what to multiply that row by and subtract it from. This is equivalent to doing the shears without doing all of the matrix multiplication, which is expensive because you have all those rows and columns not doing anything. This literally is just doing the multiply and subtract the rows, update the element of bi the same way, and then go back up for the next element of j and go through the rows. So after you've done this, all of the elements below the diagonal will be set to 0 and the matrix will be upper triangular. Now, that's just to give you a good idea what the algorithm is. I don't actually suggest you implement it that way. There's a bunch of special details for stability we'll want to talk about, or you could talk about in another class. We're not going to talk about it here. Given that, we just do our back substitution, which is relatively simple. You'll notice that in the substitution, in the operations here, we're subtracting off weighted multiples of the matrix and doing it from the right-hand side. It's actually a very common programming convention to build what we call the augmented matrix, where we write the main matrix augmented with B on the right-hand side. So now I just do the same operations down the entire row, including the extra element for B. If we want to look at the forward elimination written in matrix form to produce the zeros, we can actually view all of these as a sequence of shear elements down this stuff below the diagonal. So the elements of GIs are multipliers. G sub j is called our Gauss matrix. And so we can view the sequence of getting G of permutation if we need one, or pivot, G1, pivot 2, G2, up to Z. And if no pivot is necessary, it's possible to actually store the elements back in the matrix. For efficiency, we don't explicitly actually ever multiply it this way. This is just a way of looking at it. You'll see why in a second we wanted to look at it that way. Before we do, let's talk about its computational efficiency. So one of the issues we get is that this requires a lot of work. Overall, the Gauss elimination requires O of n cubed operations, where our matrix was n by n, which is okay if n is 1,000, but it's not suitable at all if we have millions, because a million cubed is just too large. So when the system becomes very large, very often when they're large, in fact, the matrix tends to have lots and lots of zeros in it. If you think about the link matrix we saw, for example, for the web, most web pages are not connected to most web pages. They're connected to 4 or 5. So every row has 4 or 5 entries in it out of a million or a billion columns. So it's a very sparse linear system, and there's a much better set of techniques called iterative methods to solve those. We're not going to go in this chapter. We'll talk to those at the very end of the semester. So now we're going back to a special case. We want to solve a equals 0. Of course, we can always have the trivial solution, but that's not of interest. So the question is, how do we use Gauss elimination to find if a non-trivial solution exists? And any non-trivial solution u will mean that c times u is a solution as well, because obviously I can multiply everything by c and it'll still say 0. And so the way to solve this is we do the same forward elimination, but we make a slightly modified version of the back substitution step. So we do our Gaussian elimination, and so, for example, in this matrix here we have 1, 2, 3 for the entire matrix. When we do our forward elimination step, we get 1, 2, 3, and everything else becomes zeros. And some of you may remember seeing things like this when we were working on eigenvalue problems because some of the rows disappeared. So to solve for these, for each row of the transform system, we're going to set the UI associated with the free undefined rows to be free variables to 1. So in this case, we're going to look at this and say we're going to set these last 2 elements to be 1. And then we can put them back into this equation, and we can see that what do we have to set this first value to? Well, if it's going to be 1 times the first value plus 1 times 2 plus 1 times 3, this first value has got to equal -5 so that this first equation is satisfied. And then any vector of the form cu, where this is u, is also going to be a solution. So this gives us a way of getting solutions in that last case. So in that previous example, we had a 3 by 3 matrix, but it was of rank 1, which means we have a 2-dimensional null space. And so now we can ask the question, how do we span that null space? So the number of free variables in this equation, right, the number of rows that were exactly equal to 0, give us our null space size. So we're going to systematically construct 2 vectors that span the null space, and the basic idea of that is to set one of the variables to 1 and the other to 0. So we're going to take those last 2 rows, which we knew were going to be free variables. We'll set 1 to 0, 1 to 1, and then to make our thing satisfy our first equation, we have to fill it back in, and we get that u1 has got to be -3, 0, 1, and then u2 will be -2, 1, 0. And then all linear combinations of the null space are also in the null space, so we can write any linear combination of these two to completely span the null space. So given what we get out of Gauss elimination, by figuring out what are the free variables, initializing these to 1, we get solutions to both the homogeneous case, and we can get back from that our system of the null space. Now, one of the other problems we might run into, especially in systems that have zeros, is a homogeneous problem where some of the diagonals become 0. So, for example, we might end up with something that looks like this, 0, 6, 3, 0, 0, 2, 0. The question is, can we solve this one? Well, if we just try and look at this, we have a problem. But instead of applying row pivots, we can do column pivots as well. Notice when I do column pivots, it's important to recognize that I've changed the order of variables. Right? Because in this matrix, the fact that they're all zeros on the diagonal are just because I wrote them in the order U1, U2, U3. If I had written them in the order U2, U3, 1, I'd have this matrix. So here, when I do a column pivot, I have to reorder the variables, which means I have to be very careful when I go to do back substitution. Now I have this. I can notice that there's a free variable, solve for it. So I can set the free variable back and then substitute back in, and I get that the solution to this problem is all vectors of the form C times 1, 0, 0. Okay, and again, why is it 1, 0, 0? When here you're looking at this and seeing 0, 0, and it's the last row? Because this last row is associated with U1. We reordered them, so here we're putting them back in the original order of U1, U2, U3. So in class, we've talked a little bit about inverse matrices. They're really primarily a theoretical concept in general. You could solve AV equals B by saying V equals A inverse times B, but you really don't want to do that. It's a very expensive way of computing it. Gauss elimination, or LU decomposition, we'll talk about in a second, is much cheaper. Forming the explicit inverse, you can do it. You do forward elimination, you do n back substitution algorithms, and you get matrix vector multiplication. In fact, I can do the inverse by basically building a right-hand side for B. Instead of B, I can put the 1, 0, 0, 0, 1, 0, 0, 0, 1. I can put all the primary unit vectors on the right-hand side and solve a whole bunch of equations. And then I can get the actual inverse. But it's expensive and numerically unstable, so just don't. The inverse exists if the n by n matrix has rank n. It's a full rank. The action of A doesn't reduce dimensionality, so all columns are linearly independent. So if A is invertible, we can always do Gaussian elimination. A becomes upper triangular with all non-zero elements, becomes invertible. Otherwise, A is singular, right? So if, as during the Gaussian elimination process, we run into a zero diagonal, and I can either do a row pivot or a column pivot, then I will I'll know my matrix is singular. So coming back to rank, to sort of a quick review of it, matrix doesn't reduce dimensionality, so anything I do in terms of adding rows, subtracting rows, that keeps the rank the same. So something will be of rank n or full rank if it's invertible. A matrix that does reduce rank by dimension k will have rank n minus k. It's a projection, getting rid of k dimensions. The n by identity matrix has rank n, the zero matrix has rank 0, the identity matrix in rank in n dimensions is right here, right, has rank n. Okay, so now let's look at combining a bunch of Gauss eliminations. If I want to solve not one equation, but a lot of equations, we're going to use this thing called LU decomposition. So going back to what we saw, we actually could view our steps for solving Gauss elimination as A times pivot 1 times G1 times pivot 2, G2, dot, 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 to Gn. If we forget pivots for a second, then I can represent this just as this product of matrices. And if you remember, each of those matrices was in a sort of bunch of elements in a column. And it turns out that that matrix is a lower triangular matrix. If I take the product of all these, and I don't even have to multiply them because they're all some things below the diagonal, and either the identity matrix is 0 or everywhere else, I can just sort of copy all the values together, and that gives me this lower triangular matrix L. And that matrix times U is equal to A, right? So if I start with some right-hand side U, right, G times all of these times A, so A is equal to G times all this stuff. U is the upper triangular matrix we got after a Gauss elimination. All this other stuff is a lower triangular matrix, and we call this process then the LU decomposition of A. It's also called the triangular factorization of A, and there's some other variants that we can talk about. Every matrix that is invertible has such a decomposition. Okay, pivoting might be necessary, in which case we have to be a little careful how we represent the pivot matrix, but it always has an LU decomposition. So for a simple 3x3 matrix, we can sort of see in general, if I take U11, U12, U13, the rest of the elements of a diagonal matrix, and I take this lower triangular matrix, when I go to multiply these out, right, the structure is such that I'm taking this row times this column. So that gives me U11 is A1. Okay, the next row I'm going to get L211 times U21 gives me A22. So the structure of L times U gives me back all the original matrix elements, but there's lots of zeros and lots of ones. So we saw how the upper triangular form made it easy for us to do back substitution. Well, it turns out that if I view my LU decomposition, I can write my matrix as LUA equals B. And now, just do a change of variables, I can solve this as a two-step process. Let's solve the equation Ly equals B. And then, given that I've computed y, I'm going to solve, I'm going to let y equals u times u, right? U is an unknown, so I can't really multiply it that way, but logically I can say, imagine that u is y, then I can solve Ly equals b. So now when I have y, I can go back and say y equals uu, I can solve for u. Now, because L is a triangular matrix, right? It's not the same triangular matrix, it's a lower triangular matrix with ones on the diagonal. It's actually really easy to solve Ly equals b. This is just like back substitution. It's just lower triangular back substitution. And then, so we just sort of, we call that forward substitution because it's going down the rows. And then we do back substitution up the rows of u. So after we've given the LU decomposition, you give me a right-hand side. It's really easy to solve this because it's basically just forward substitution, back substitution. Example, just to show you what an LU decomposition might look like. So here's an actual matrix. It's described in the chapter if you want to go through the individual steps. You do the LU decomposition, and we can verify that we get the following two matrices multiplied back out to this. And if I want to solve using this, I take Ly equals b. So I do solving for y1, y2, y3. I take this lower triangular matrix equals 1, 1, 1. I get, obviously the first one is 1, then I back substitute in and I'll get 3/2 and then 0. Given that I have this, then you can do back substitution and solve u times u equals y. So I do back substitutions with this as my right-hand side now, not b, but y is my right-hand side, and I get u equals 0, 1/2, 0. And it's actually easy to check that A2 is in fact a multiple of B. Go back to our solution here, right? Here is B, here is A2, right? So it's not surprising that our answer was, forget these columns, just use A2. Okay, so now let's come back to dealing with pivoting. So suppose A is non-singular, but it does need some pivoting to make this work. Then a permutation matrix can be used to exchange the rows. So we can think of a permutation matrix times AU equals a permutation matrix times B. And then we'll find that P times A equals LU. And in fact, P can be a permutation that does all the permutations we need to put all the columns and rows in the right order. So the major benefit of LU decomposition is speed. Once we've done it, especially if I want to solve the same right-hand side multiple times, it's really a much faster solution. So if you're going to do that, you construct the forward decomposition to get LU, and then you can do back substitution to get right-hand sides. In fact, if I want to find the inverse of a matrix, this is the faster way of solving it. Do LU, and then apply it to the first basis vector 1, 0, 0, and then 0, 1, 0, and that'll give you back the inverse. Still don't recommend you ever use the inverse for anything, but theoretically that's a reason you might solve it. But if you imagine that A was describing some, say, production of how I should allocate resources today, and the right-hand side was available staff, then every day I might want to reallocate work, then I could solve the LU decomposition, which describes the sort of structure of my company every day. Given a set of right-hand sides, the available work for today, I can then get the assignment out of it. Just coming back to relate a few things from the chapter in terms of determinants. So we already saw in 3D the triple scalar project. We talked about the more general form of n by n determinants. There's lots of ways you can do it. You can talk about cofactor expansions and whatever. I strongly recommend you don't worry too much about them. If you ever need to compute them, you'd want to actually compute them in terms of looking at A transformed to upper triangular form by Gauss elimination. Those sequences of shears and row exchanges don't change volume. Shears don't change volume. Row exchanges change the sign, so it depends on how many of those you do. But when you get done counting for the right number of row exchanges, you basically take the product of what's left on the diagonal. That gives you the determinant plus or minus the sign. So minus 1 raised to the number of row exchanges times the product on the diagonal gives you. This is one of the best and the most stable methods for computing the determinant. If you really want to do that, that's the way you would get it. Libraries, of course, exist, so if you really need the determinant, call it a good library. So the idea of cofactor expansion, we talked about briefly, is mostly a theoretical tool. It's really not something you would ever want to do. Similarly, we talked about Cramer's rule, where you deal with it because you have to look in Cramer's rule of taking the determinant of A1 divided by the determinant of A. In the cofactor expansions, one of the reasons this is a really bad idea is this determinant of A might not be 0, but it might be a really small number, which means when you divide by it, bad things happen and stuff blows up. So Cramer's rule is mostly a theoretical tool. It is useful for 2x2 and 3x3 systems if you need to do stuff by hand. As we generalize to higher dimensions, you wouldn't want to do it. Again, for lots of this stuff, you shouldn't be implementing Gauss elimination or determinant calculations. You should find a good software library and have them do it for you. But it's important to help you understand the concepts. So now let's get to a very important application area of linear algebra, which we call linear least squares. So if we're presented with a lot of data and we want to have a nice way of simplifying it back to a model, what do we want to do? So if, let's say, for example, here we have AIG, one of the people who were part of the bank crash in 2008, or so the market crash. If we look at the stock price, it's clearly trending downward, but how do we define what that trend is? So we can think of this as a best fit line approximating the data. And of course, I could do it for stock prices. I can do it for anything. It doesn't mean because I can fit a line, the line is a good thing, but if all I want is a simple model, the simplest model is linear. And at a deeper level, locally linear stuff is really interesting. Newton was actually famous for having said that in the small, everything is linear. Newton helped invent some of the differential calculus stuff. And when you look at things in the very small levels, we'll like to use linear. But the data itself doesn't always fit the data. So we have to have some way of talking about how we approximate stuff when they move up or down. Data can be noisy. And so I don't want to necessarily just draw a line between each piece of the data. What I want to do is find a way of getting rid of that noise. And noise might be from how I encountered data, some observation methods lapse. So, I made a mistake when I'm writing numbers now, round off error, all kinds of things. And given that I've got some noisy data, I want to summarize the data, maybe estimate values where the data is missing. That's all pretty good. Predicting the future is possible, but to use with a linear technique, but it's not necessarily a good prediction of the future. You can always say this is what we think will happen. So if we think of this very simple set of data, here we have data at various times as something is cooling down, and then its temperature. So it starts at 30, 25, 40, 40, 35, 25. There's a little bit of random variation what these temperatures are, but we can say overall what's happening to this temperature, and I can ask for the linear trend that explains the data. So to do that, we want to find a simple linear relationship. So I want to think of temperature is equal to A times time plus B. And if we write down the relationship between the known and unknowns, I'm going to get a matrix equation, but I'm going to have a lot more rows than I have columns. So I'm going to have 7 rows and 2 columns here. And now I have what we call an overdetermined system, 7 equations and 2 unknowns. In general, the solution is not going to have a solution. It might. Remember, we already said that no matter how many columns I have, if I can write this as an exact linear combination of these, this solution will exist. So in general, this solution will not exist. It will be inconsistent. But we can ask a very important question. Can we find an approximate solution? That is, what's the best approximation to these? So what do we mean by best approximation? Well, this leads us to the idea of a least square solution. So I can actually get there in one of two different ways. I can represent this as, let's say I wanted to find the AU, the U, such that when I take AU minus B, and I do this sum of the squares of all those elements. So I multiply these all out, and then I take the difference between what was predicted and what was recorded, and I take the square of that error, so it doesn't have we don't have to worry about signs. Sum of them all up, sort of squared error, mean square error. I can ask what's the best solution in terms of mean square error, and it turns out that's the same as least squares, which is what we're going to look at. We're going to look at it in a more geometric concept. So if I have to have a solution that does exist, so I have two column vectors, A1 and A2, and again, they can be in more dimensions, but we're just going to do them in 2D, then if I'm going to write something as a linear combination, then I have to represent it in this plane. And so now B is this vector, so what I can ask is, what is the shortest vector that projects the end of B into this plane? And we know that the shortest vector is going to be the orthogonal projection on that plane, so it's perpendicular here. Any other point on this plane is farther away from B than this point B prime. And so even though it's unsolvable, we want to represent our solution as the sum of two things. B is going to be a component in the plane plus a component perpendicular to the plane. And of all the points in the plane, B prime here is the closest. Why? Because as I get farther away in any other direction, I'm going to increase the length of this triangle and make it bigger. So since we know that B orthogonal is orthogonal to V, we can actually write down a couple of equations. We can see that A1 transpose times B is equal to 0. That's just the dot product. And if it's orthogonal, we know it's 0. And A transpose B orthogonal is equal to 0. We can put those two column vectors back together into a matrix, which is now actually much wider. It's A transpose. So this has got 2 rows and 7 columns. Times B is equal to 0. Okay, and now we can look at this and say, okay, we can solve this. Well, we might want to solve this, but it's still not square. So let's look at it slightly differently. We also know that B transpose, or sorry, B orthogonal is equal to B minus B prime. So if I just put B minus B prime back into this equation of A transpose B orthogonal, we get A transpose B minus B prime equals 0. But we already know from where we started that B prime is just A times U. So we're going to go see that this is A transpose B minus A transpose A U equals 0. Rearranging this, we get that A transpose A U equals A transpose B. So if you think back to your eigenfaces, you'll sort of start to see that this is somehow related. These are what we call the normal equations. And for a linear system with a square symmetric matrix, this is always a linear system with a square symmetric matrix. A transpose A will be square and symmetric, right, because we took the transpose and we multiplied it. So turns out, as we sort of described here, of all the points in this plane trying to stay the closest, right, that is AU, our actually projection, minus the actual B, and we can think of the square error between that. So that's why we call this least square solution. This was, depending on how you want to believe, it was either Legendre or Gauss. Gauss claims earlier work, and this was very instrumental in Gauss's earlier estimations of elements of the solar system and where planets would be in a future time. So coming back to that example, if we had this original matrix of the times, right, from our model, here we have the actual time, that's T, and then here we have the constant 1, times AB equals our temperature. We now take A transpose A, and we get the following much smaller matrix, 9100, 210, 210, 7, right, it's symmetric, equals this. Now I solve this 2 by 2 matrix, and this allows me to get a fitting for a line. Now, one of the reasons that this was invented back in Gauss's day is this also was really important because here I might have hundreds of observations, but they might be noisy observations. Imagine you're trying to estimate where a planet or a comet is. So you're watching something in the sky and different people are estimating. You get lots of noisy estimates of where they are. But you can put them all together and build a model. Here the model is a line. We'll talk a little bit about nonlinear models in just a second. But by doing lots of those noisy measurements, you can get a line. But it's also nice because all I have to do is take this transpose product, which is pretty simple stuff to do by hand, because back then they didn't have computers or calculators, And now I have a 2 by 2 matrix, which we know how to solve by hand, so we can get a solution to the overall equation pretty easily. So in real-world problems, we have to be very careful because when we have noisy data, there might be some data that's really way outside our norm. We call these kinds of points outliers. In fact, if you looked at this data here, this one point down here looks like it might be an outlier if this is temperature, although if you live in Colorado, you would recognize that you could have temperatures of 70 one day and 10 the next. That's just Colorado. But for most people, this temperature down here would be an outlier. So then we can talk about other techniques that can be very neat, where we can trim outliers and do stuff. That's beyond the scope of this class, but we can talk about trim tail least squares. There's also partial least squares. There's a bunch of other techniques. We're going to look again at this next week when we talk about some ideas from householder methods, which are a little bit more efficient, and SVD, which is my preferred way of solving lots of these least squares problems. One of the reasons is you have to be very careful. When I take A transpose A, this matrix here, while I can do it, it's actually going to be numerically unstable. We'll have a lot more round-off error. So in general, we don't actually solve A transpose A if we have a computer. We're going to do SVD or householder techniques. Just to give you a quick idea of some more realistic applications that might use this. So let's imagine that you're trying to work with a group that's trying to figure out how to replace somebody's hip. And the hip implant thing, a femoral head, is this round, it's a spherical socket, which is the joint for the upper part of your hip, that's going to go into your hip, and then a shaft that goes into your existing femur. So getting this sphere right to match your personal hip, or your grandmother's hip, if she's the one being replaced, is really important. So you're going to collect by measuring with an MRI or PET scans a bunch of points that just help describe the ball socket of their hip. And then you want to fit a sphere to this, and then you can figure out how to manufacture the transplant. Now, here we're doing it as a sphere, which is the simplest model because you only have one free parameter. So given a set of vectors in 3D, V1 to VL, of approximately equal length, you want to find a sphere centered at the origin with radius r closely fitting these points. So we have a bunch of points. We've already computed the center, and then we want to figure out what's the best radius of the sphere to approximate that data. So if I'm going to do that, my model is actually very simple. It's just r. So when I have it for each of the data points, I have 1 times r. Is this, whatever. So this is a very overdetermined system. We have L equations and only 1 unknowns. And if I multiply both sides of this by 1, take the transpose, right, that's going to give me that L times R is equal to rho 1 dot 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 up to rho to L, so that R is equal to all of my measurements divided by L. So in this case, the least squares solution is simply the average of the given radii, which might have been your first guess. How would you solve this? But if we had more complicated data, as we'll see in a second, it becomes harder for us to see exactly what this will be. So the whole point of least squares is this gives us the intuitive answers when you expect it, but now let's look at something else. Let's go back to that polynomial we talked about. Well, it turns out that polynomial fitting is numerically a really bad, it's unstable problem, especially if you try and get to a higher order polynomial. So if I actually had 9 measurements, I wouldn't want to fit a 9th degree polynomial because it'll wiggle like crazy through all the data. I might have a reason to believe I have a 4th order model. So what I do is I build the same kind of matrix where I take T1, T0, Ti squared, Ti cubed, Ti fourth, my model matrix, my coefficient matrix, and I put that down for each row. And now, of course, I get a low, I can solve for this by doing A transpose A and solve for my coefficient. And at 4, if this data is reasonably well behaved, you might still be able to do this. Numerically, it'll be better to use SVD. But again, I just want to see, this is how we deal with larger problems. We write down our model. Our model is some constant times some function plus another constant times a function plus another constant. The functions are evaluated at each of the data points where I have my right-hand side. And then, so I have these times these coefficients have to equal this. This is why we call it linear least squares. Our coefficients are all linear. Our model might have nonlinear terms in it, but that's okay. We're then going to fit to this data. So now I want to come back to the example of smoothing tessellations. In fact, your final programming assignment will be doing some tessellation-related work. So again, imagine that I have some triangles. Now I want to come up with a better triangulation that's smoother. Sorkai in Cohen-Orr came up with a nice solution called, in their paper, least squares meshes, and there's lots of other variations. But basically, they define a graph where I look at the connected neighbors and then I define penalties depending on if the edge is good or if the edge is bad. Then I can put in some different penalties. And then I say some of these can move and some of them can't, and then I let the system try and solve it. And if you read through their paper, and you will, you'll find that eventually this system is solved by in a least square sense. So they want to find the value of x, where A is this matrix that defines all these constraints, AX minus B, where B is a set of right-hand sides they're going to get from the original graph. They describe it in a different form, and they show that the unique analytical solution is A transpose A inverse times A transpose B, and they get the extra set of these because, right, they're going to do our A transpose A on both sides, and then multiplies inverse. Now, pragmatically, again, we're not going to do the inverse. We're going to solve for it explicitly, but this brings back the whole large linear systems occur because we might have millions of triangles representing some complex shape, and then I want to smooth them, and very often I also want to simplify them and get rid of some of them, and those are all interesting questions that lead to large linear systems. So at the end of chapter 12, you'll find a bunch of questions in the book, some of which I've answered in the back. You should go through some of these, prepare for the general least square. So there's a lot of terminology in this chapter. Make sure you know the definition of each of the words you should know. While I might not expect you to be able to implement Gaussian elimination in detail in terms of code, I do expect you to be able to talk about Gaussian elimination, forward elimination, the coefficient matrix, the augmented matrix, any of the terms on here. There will be plenty of those kinds of questions on the exam.